Okay, before we get to the answers to these questions, I don't know why I didn't think of this earlier, but I didn't. But I did it last week. On Google Classroom now, I have put a Google Docs version of the notes packages. That means if you put that on your phone, you can actually modify it on your phone using the Google Docs app. Okay, so if you want to do that, that's entirely up to you. If you haven't already printed the whole thing, or if you've been just looking at the PDF this whole time and having to scribble stuff on paper, okay, this will allow you to do it completely electronically if you want. Okay, so if you are interested in that, where you can find it is on the About tab. Okay, so when you're in Google Classroom, go to the About tab, and you'll see here that I have it organized by unit. Okay, so I've got the biology one, the chemistry one, physics here, okay, and so on. If you open that up, if you click on that, okay, it'll open it, but it'll say view only eventually, okay, which means you can't edit this one because it's mine, okay. What you have to do is just go File, make a copy. Okay, you make a copy for yourself, you rename it something else, and you can modify it, you can type into it on your phone. Okay, if you want to add stuff, you can put comments in the margins, just like I do with your labs. Okay, all of that kind of stuff. If you'd rather do it that way and always have that electronic version, you are certainly able to do that. A bunch of people, I guess, are already doing, because I can see them signed in up there. Okay, but yeah, so that's entirely up to you if you want to do it that way. If you don't already have it printed on paper, or you don't, whatever, it's an option. Anyway, you just make a copy, okay, and you're good. Okay, just make sure you remember where you save that file, and then if you have the Google Docs app on your phone, you can modify it on your phone. Okay, so up to you, but it's another option for you. Save some paper. Okay, in terms of the questions on here, question number 2, for each of the following scientists, describe his invention, the type of energy the inventor was able to produce, and how it was produced. So let's go Orsted, let's go with Kaylee. Right, okay, so he was the one who had the electric wire that ran over the compass needle, and the compass needle moved so that it was lined up with the wire. Okay, so essentially he discovered the relationship between electricity and magnetism. That is, that a current carrying wire makes an electromagnetic field, or a magnetic field around it, okay, that can disrupt a compass. Okay, in other words, he invented the first electromagnet. Okay, that was really essentially what he did. His contributions, as well as those of Faraday, okay, led to the entire science based around electromagnetic properties of matter. Okay, that allowed us to invent things like radio transmitters, radio receivers, okay, microwaves, anything that uses essentially an electromagnetic disturbance, okay, or creates an electromagnetic field. Right? So Faraday, his experiment was the exact opposite. Okay, where Oersted discovered electricity has magnetic properties, okay, Faraday discovered magnetism has electric properties, and that's how he invented that first generator with the magnet that was moving through the coil of wire. Okay, as it went through the coil of wire, it pushed the electrons through, okay, and made an electric current. All right, what about Seebeck? Right. Okay. So Seebeck invented the first thermoelectric converter, or thermocouple. Okay, showing that as long as there was a difference in the rate at which heat could travel through materials, he could make the electrons move, okay, and generate an electric current. Is it very efficient? No. Okay, you don't get very much electricity out of a thermocouple. It's mostly used as a circuit breaker, okay, things like that. And I believe in the podcast it also mentioned that they have them in the brake rotors of some hybrid vehicles. That is so that when you apply the brakes, the heat generated by the brakes, some of it gets turned back into electricity that gets sent back to the batteries. It just makes them a little bit more efficient. Okay, but it isn't something that we're going to readily use to generate large amounts of electricity, because it's just not very efficient. Okay, what about Edison? Jaden, what did Edison discover? He was the light bulb guy. Thomas Edison invented the first incandescent, tungsten filament light bulb. So he was able to convert electricity into heat and light with his invention. All right. Eventually, after like 1,000 different variations on the original, okay, Edison's kind of the eternal optimist. When he was interviewed by newspaper people after his invention, they asked, like, did you ever consider yourself a failure? You tried like 1,000 times to make the tungsten filament light bulb and you failed. And he said, no, I found out 999 ways not to make a light bulb. He's one of those like really annoying glass half full people. Okay? It's just always cheerful. Anyway, okay, he did eventually come up with a solution, which was you have to remove all the air. Okay, essentially a light bulb is a vacuum inside, because if there's any oxygen in there, the tungsten filament just burns up instead of glowing. Okay, and that was kind of the biggest obstacle to the invention of the light bulb. Okay, but it did convert electricity into heat mostly and light. All right, what about Volta? Okay. Right. Okay. He invented the Volta pile, which converted chemical energy into electricity, essentially the ancestor of the AAA battery. Okay. Dry cell, because it didn't involve any fluids. Okay. There was moistened paper in between the different metals. Okay. But it's essentially just a dry cell. Okay. That we now use, obviously, to power all kinds of electric devices. Okay. Was his rechargeable? No. Okay. For number 3, okay, we kind of already talked about that. What do we use each of those for today? Okay, number 4, what's the difference between nuclear fusion and nuclear fission? Gabe. Right? Right. Okay. So nuclear fission involves splitting a very large atom into many pieces. Okay. It's not always directly in half, because we're not nearly that accurate. It's mostly if you get a few of the like uranium or plutonium atoms breaking, their pieces go off and break other nearby atoms, and you get this kind of chain reaction. Okay. So it's essentially splitting of the atom or breaking of the atoms, whereas fusion is forcing small atoms together to form slightly larger ones. Okay. Now, how are they similar? They both release the energy that holds atoms together. Okay? There is this electromagnetic energy that keeps positively charged protons and negatively charged electrons, around each other in the area of the atom. Okay? And when you change the structure of the atom, some of that energy gets released. Okay, if you're splitting it, obviously you're breaking the atom and it's not holding itself together anymore. Okay, and with fusion, you're altering the arrangement of the particles, putting more in there, and some energy is released on that as well. Okay, what is the modern theory of the source of energy for the sun? Let's go with Ethan on that one. Give it a try. We may have just been talking about it. No, where do we get the solar energy from? Why does the sun give us solar energy? What's going on the sun? Nuclear fusion, right. Okay, the sun is a big giant ball of hydrogen. It is incredibly massive. It has so much mass that its gravitational pull is strong enough to force hydrogen atoms together into helium atoms and release the energy as a result of that reaction. That'll last for a while. Okay, eventually the sun will run out of hydrogen. And it's big enough that it'll start to fuse the helium atoms it has left behind. When it does that, it's going to swell. It's going to become a red giant. It will swallow up the inner planets, probably get out to about where Mars is. Okay, certainly Earth will be swallowed up at that point. And as it fuses helium, it'll start to create heavier atoms as a result of the fusion. The sun doesn't have enough mass to continue to fuse those. As a result, its fusion reactions will slow. Okay, and it will shrink, and it'll go down to a little tiny pathetic white dwarf at the center of the solar system that just kind of glows and doesn't really do much. Okay, but that you don't have to worry about. That's not going to happen tomorrow or the next day or 200 years from now. It's good for a couple billion years. It's practically still under warranty. Okay, so we don't have to worry about the sun running out of fuel anytime soon. Okay, but it will eventually. All right, number 9, describe the contributions the following people made to the nature of heat. Okay, Spencer, what did Sadiq Carnot find out? Right, yeah, sorry, go ahead. Right. Okay, Sadi Carnot discovered that you could turn thermal energy, which we commonly call heat, which isn't really right, okay, but that's what we call it. He discovered that thermal energy could be converted to mechanical energy. It's not easy, it's not terribly efficient, but it can happen. That means we can take thermal energy or a hot object and make it do useful work. That is, cause movement, okay, of some kind. All right, so anyway, he showed there was a relationship between the two of them. What did James Young do? Bree, what did James Young do? Right, okay, he's the one who discovered mechanical energy has essentially two forms, potential and kinetic. If something is above the surface of the Earth, it has the potential to fall, okay, and if it falls, it can be turned into kinetic energy. Both kinds then add up together. Okay, what about Joseph Black? Let's have Lucy tell me that one. Okay, so he discovered that if you put a cold object inside of something hot, the cold object would get hotter. In other words, he discovered the direction energy flows. Specifically, thermal energy always flows from a hot object or high energy object to a lower energy or colder object. The same is also true for mechanical energy. Okay, a higher energy object with more mechanical energy can transfer energy to a lower energy object. Okay, that is possible. All right, and then Count Rumford. Why anyone would change their name to that, I don't understand. Let's have Sarah tell me that one. Right, he suggested that the motion of his workers who were making cannons, okay, could manufacture heat. In other words, the opposite of what Sadi Carnot discovered. Okay, Sadi Carnot said heat could turn into mechanical energy. Rumford discovered the opposite is also true. Okay, that the movement of his workers in turning these boring drills, okay, could generate heat in the copper and eventually make it so hot that they could boil a kettle of water on top. Okay, their movement, their mechanical energy was being turned into heat as a result of all the friction that was going on between the drill bit and the metal they were boring into. Okay, number 10. So this is about Jules' experiments here, these two diagrams. Okay, Joule was trying to show that potential energy was a real thing. In order to do that, he had to show it doing something. He had to show it being converted into a more measurable type of energy, right? Because it's hard to say that an object held above the ground has energy, because it isn't doing anything, okay? Now, we know in kind of modern times that the only reason it gets up above the ground is because somebody did what? Somebody lifted it, okay? If you lift it there, did you do work? Yeah, okay, so you gave it energy. That's what work is. Work is the transfer of energy. We're going to talk about that later today. Okay, so it only has energy because it's been taken to that point. But what he did is he showed that that potential energy could be released and it could be turned into heat. Okay, so he had these two experiments. I think the block experiment is a better example of what he was trying to prove. Okay, but they're specifically asking about this setup with the masses and the pulley and the little metal fan blades, okay, that are inside this jar. So he would set the apparatus up. These two weights would have potential energy because they're above the ground, and when he lets them go, they'll fall. Okay, as they fall, they turn this pulley, okay, and that makes the fan blades inside spin. Anytime you move something through air, okay, is there resistance? There is. Okay, and as a result of resistance, we call that resistance friction. It's air resistance, but it's still a form of friction. There's going to be sound and heat produced. Okay, those are evidence, because they're forms of energy, that there had to have been some energy initially. The energy to make sound and heat had to come from these two falling weights. Okay, that's what he showed with that. And it was the same thing with the falling block. Okay, moving the falling block up to here involved him using some of his own energy to give it potential energy, and when he let it go, it fell down and slammed into the stationary block. And when it slammed into the stationary block, the temperature of the stationary block went up. Was there any other evidence that there was energy there? The sound, yeah, that thwacking sound that two pieces of wood make when you smack them together, okay, certainly would have also been evidence that there was energy involved up here, okay. All right, number 12. Given the following situations, identify the major form of energy involved. So you put an antacid tablet in a glass of water, and the tablet starts to bubble. Ben. 12A. Okay, give it a try. If I put an antacid tablet in a glass of water, it starts to bubble. Bubbles are a sign of a, think back to Unit 1, of a chemical reaction. Okay, so this is chemical energy. Right, there was a higher state of chemical energy before. Okay, now there'll be a lower state of chemical energy after. Okay, there's energy being released by the reaction between the antacid tablet and the water. All right, this is something you'll learn about, and I think it's Chem 30 when you start talking about entropy and enthalpy. Everything has a certain amount of chemical energy in it, and after a reaction, that energy changes, and the amount of energy released can be calculated as the enthalpy of that reaction. That's how we design fuels. Okay, we only want fuels that are going to give off large amounts of energy with low kind of investment. Okay, a fluorescent dial on a wristwatch glows at night. Jordan. Okay, so if I'm outside and my watch is in the sun, then I come in and I put it in the dark, now it glows. Where did it get the energy from? Fluorescent objects absorb energy from the sun. So we're talking about solar energy here. Okay, it's solar energy because those fluorescent things, okay, their electrons get excited when the light strikes them, and they continue to give off that light once I remove them from that high energy environment for a little while, not forever. Okay, and we're talking about the fluorescent part, not the light that you can activate by pressing the button on your watch, okay, because that's draining from the battery. That's chemical energy. We're talking about the fluorescent parts of the watch that only glow for a short time. Okay, C. A downhill skier begins to ski down the slope with increasing speed. Kylie. Motion and energy. So what kind of energy is that? Starts with M. Mechanical. Yeah, mechanical energy, right? Because he's got potential at the top, kinetic at the bottom. Okay, those two things go together as mechanical energy. Okay, for D, this is how back in my day we used to test whether a 9-volt battery was any good. Okay, I don't recommend it. If the battery is dead, you get a slight tingling sensation or nothing. If the battery is really good, you get 2 little marks on your tongue where it like cauterizes between the two things. It's not really a good way to test a 9-volt battery. Okay, it was what we had, but you guys probably have way better ways to do that. Now even they come with a little tester right on the battery themselves in some cases. Okay. So what gives you that? What kind of energy would cause that? Electrical energy, yeah. Okay. Okay. Inside of a car gets extremely warm if the car is left in the sunshine. Will. Okay. There's going to be some thermal wear from the solar. Yeah, from sun. Okay. Essentially, a car is a greenhouse. The light can come in through the glass. Okay, but once it goes through the glass, its wavelength gets altered slightly. It bounces off the inside of the car and can't escape back out through the glass. So it bounces around inside the car for quite a while, warming up the inside of the car, just like a greenhouse would. Okay, a seagull lifts a clam high above the beach. Let's have Rachel tell me this one. Potential energy, yeah, it's above the ground. If it's above the ground, it can fall. That's gravitational potential energy. Okay, could we also say it's mechanical energy? Yes, because if you have either potential or kinetic, you have mechanical. And G, a compass needle held over the surface of the Earth points north. Tuscany, what kind would that be? Magnetism, exactly. All right. For 13, describe an appliance or machine that for its operation requires the following forms of energy. Chemical energy, anything that uses fuel or batteries, okay, would be running on chemical energy. Chemical energy is where the electricity comes from in a battery, okay, and then anything that burns fuel, obviously that's chemical energy as well. Okay, we are very, very dependent on chemical energy. In fact, there's no way you got to school today without it, even if you walked. Okay, because you still had to use the chemical energy in the food you ate to get here. All right, light energy. Anything that runs on solar power would require light energy. So if you have a solar powered calculator, or if you've got one of those little solar powered cell phone chargers, okay, I've seen those on people's backpacks. I've seen them on like Geek and eBay. They're just this little solar panel about the size of a cell phone that hangs off your backpack, and if your phone dies, you can plug it into this little battery that charges off that solar panel. Okay, anything that uses the sun, obviously, for energy. Okay, heat. Right, so needs heat, anything like a thermocouple, okay? Anything that uses a thermocouple would be using heat as a form of energy. Harder to think of things for that because we don't have a lot of devices that actually use heat to get going because it's not an efficient transformation. Okay, electrical energy, anything that plugs into the wall, okay? So blender, toaster, hair dryer, okay, whatever. And then magnetic, obviously a compass would be one of those, okay? An electromagnet, a transmitter, okay, radio transmitter, the remote, okay, for your TV, okay, uses electromagnetic waves to signal your TV, okay, things like that. All right, describe an appliance or machine that produces the following forms of energy. Okay, I would always say plants for A, but that's not really a machine, okay? But a plant can produce chemical energy as a result of what it does, photosynthesis. There aren't a lot of machines we have that produce chemical energy. A lot that use it, but not a lot that produce it. The only thing I could really think of there would be like a place that makes batteries, or a place like a oil refinery. It might, as its end product, produce fuel, gasoline or something. Okay. Light bulb. I don't know, that came to mind right away for some reason. Okay. Anything that glows, okay, even the screen on your cell phone, right, would be using that. Or would be producing that, sorry. Thermal energy, anything that gets hot, your stove, your toaster, hair dryer. Okay. Electrical energy, generator, solar panel. Okay. And then magnetic, electromagnet. Okay. Transmitters of any kind are going to produce magnetic energy. All right, questions on any of those? Okay. Moving on to thermodynamics. I think this is in yours. Yeah, it is. Okay. All right, so the laws of thermodynamics. What does thermodynamic mean? What does thermo usually mean? Thank you, Rachel. Yeah, it means heat. And what does it mean to be dynamic? Well, you might be working if you're dynamic, but strictly speaking, dynamic means to change. Okay. So thermodynamics is the study of changes in energy or transfers of energy, movement of energy, okay, is what thermodynamics means. Okay. So all the machines we use, okay, are governed by certain physical laws. Okay. Those laws describe the relationship between work and energy transformations. Okay. Work is a transfer of mechanical energy. So lifting something off the ground means you're doing work, because on the ground it has no energy, but when you lift it, it now has potential energy. The only way it can do that is by having work done on it. Okay. Now, in terms of thermodynamics, that's less focused on work as it is on thermal energy. Okay, so more on heat. All right. When we're talking about heat, one of the things we have to understand is what a system is and what the surroundings are, because those are terms that are going to get used together. Okay. So a system is a set of interconnected parts. Okay, very simply, it's a set of interconnected parts. So a lawnmower is the example they're going to use down there. The lawnmower would be a system of interconnected parts. Okay, so the system in strict terms is the object or objects involved in energy transfers. Okay, everything else is considered to be the surroundings. Okay. So again, the example they use here is a gasoline-powered lawnmower. Okay, the system could be the engine, and the surroundings would be the other parts of the mower, the ground, the air around the mower, etc. Okay, the set of boundaries are arbitrary. For me, when I look at that, I think everything attached to the lawnmower is the system, and the air surrounding it is the surroundings. Okay, because, well, the blade doesn't move without being connected to the mower itself. But again, they're saying the boundaries are arbitrary. You can decide what parts are the system and what parts are the surroundings. Okay, so there's three kinds of systems, and you do need to be able to identify these. Okay, the first type of system is an open system. Open systems can exchange both matter and energy with their surroundings. Okay, so right now, each and every one of you is an open system. Okay, you're breathing in, so you're taking in oxygen, you're breathing out, you're exchanging oxygen for carbon dioxide. Okay, we exchange matter and energy with our surroundings all the time. Okay, well, matter anyway. Okay, in terms of exchanging energy with the surroundings, we also do that. Okay, in fact, I depend on it entirely to heat this classroom because I refuse to turn the thermostat up in here. Okay, I use student heat to heat my classroom because if I don't, it becomes a pressure cooker in here by period 4. Okay, on a bright sunny day, the temperature in this room can reach like 28 degrees. It's sweltering, right? So I never turn on the heat because in the morning I come in here and it's cold. Well, my period 1 class, by the time period 1's over, it's like 2 or 3 degrees warmer in here already, and I haven't turned on the heat. Where'd all that energy come from? It came from every one of the people in this room because our body temperature is about 37 degrees. The air temperature when I first came in here this morning was about 19. Okay, now it's about 21. Okay, energy flows from hot objects to cold objects. Okay, that's what Joseph Black discovered. So you're the hot objects, the surroundings are the cold area. Okay, and eventually this place warms up. Okay, it works through most of the school year. When it gets really cold, don't worry, I'll turn the thermostat up. Okay, but if it's going to be a hot sunny day, and it's like November, but it's still going to be like 15 degrees today, ridiculously warm. Okay, I don't want to have that heat on in the morning because it'll get it up to 22 in here, and then I'll get all the heat from outside plus all the heat from all the students I'm going to teach during the day, and it'll be too hot to live in here, okay, by the afternoon. Everybody follow? Okay, so we're exchanging matter and energy with our surroundings because we're hotter than our surroundings, so energy naturally flows there, and of course we're taking in gases. Okay, a closed system. Okay, a closed system cannot exchange matter, but can exchange energy with the surroundings. So any airtight container is a closed system. Can something that runs on chemical energy operate in a closed system? What happens if you take a candle and you cover it up with a jar? It's burning. Sorry, the candle's already burning. It's not okay. Flame goes up. Why? There's no more oxygen. You've essentially made it now a closed system. It was open when you didn't have the jar over it, but as soon as you put the jar over it, it could no longer exchange matter and energy with the surroundings. And eventually it used up all the oxygen and went out. Okay, so a closed system is an airtight container that can no longer exchange matter with its surroundings. It can still exchange energy though. Okay, the jar would get hot, right? I wouldn't want to like hold on to it. Okay, and eventually that heat would radiate out into the surrounding area. Right? Everybody follow me there. Be like if you bought some meat at the grocery store, but you weren't going to eat it all the day you bought it. You put it in a Ziploc bag and put it in the freezer. Okay, it's going to lose energy to the freezer, but it's not going to exchange any matter because you've sealed it up into an airtight container. All right. Okay, an isolated system cannot exchange either matter or energy with its surroundings. It is essentially impossible to make one of these. Okay, we can insulate stuff, but we can't isolate stuff. Okay, it's easy to make a closed system. All you got to do is make an airtight container. That's easy, right? But making a perfectly isolated system means that no energy can escape, and that's impossible. Okay, energy is always going to escape because energy is always changing form. Okay, so like if I'm looking at this like coffee cup, it's an insulated coffee mug. Okay, if I have it completely closed, right, it's a closed system. No air gets in, no air gets out. Okay, but while it can keep the coffee warm well into the afternoon, It doesn't keep it warm forever. By this evening, I wouldn't want to drink this. Okay? Unless I was really sleepy and desperate, right? But it's going to lose energy to its surroundings. There's no way to prevent that from happening because the second law of thermodynamics says energy flows from a hot object to a cold object. And there's no way to completely isolate things from losing energy. Okay? I often have people say, well, Mr. Kutter, what about like the International Space Station? That's totally isolated. Actually, it's not. It's a closed system. It's airtight. Okay? As long as they're keeping everything there. They don't actually keep everything there. Okay? Every once in a while, they got to jettison the stuff in the space toilet, which now makes them an open system because they're now exchanging matter as well as energy with their surroundings. If they didn't exchange energy with their surroundings, they wouldn't need big solar panels on there, okay, to generate electricity and keep them warm, okay, or keep them cool depending on whether they're in the sun or in darkness. Okay, all that stuff is important to make the International Space Station run. It does exchange energy with its surroundings. Its surroundings are space. Okay? And it also exchanges matter. Okay? Every once in a while, you might see the poop meteor. Okay? Chris Hadfield was describing that when he was on the International Space Station. Yeah, every once in a while, we have to jettison the refuse container from the space toilet. So you might see a little streak shooting star. That's, yeah, the poop star, the poop meteor. Okay, it's just the stuff from the space toilet burning up in the atmosphere. That's a relatively efficient way to get rid of it. It's not going to reach the surface. You don't have to worry about that, making a poop crater anywhere near you. All right. Now, first law of thermodynamics and the law of conservation of energy. Okay, so first off, heat and work. Heat and work are different. Okay, they're different because they involve different kinds of energy. They're similar in that they're both transfers of energy. Okay, so when we say, we walk up to a campfire and we're like, oh yeah, I can feel the heat coming off of this. Well, sort of. Heat is a transfer of thermal energy. So yes, you feel heat, but you actually feel the transfer of thermal energy from the very hot fire to your very cold fingers. Okay, heat is actually the transfer of energy from one place to another, the transfer of thermal energy. So it feels hot, and that's why we describe it as heat. But heat in and of itself is not a form of energy. Even though we call it that sometimes, it's not really true. The stuff we call heat is really thermal energy. Heat is the transfer of that thermal energy from one place to another. Okay, everybody follow me there? Okay, work is similar in that it is a transfer of mechanical energy from one place to another. All right, so if I pick up something off the floor and set it on the desk, I've done work because I've taken some of my energy and given it to that object. It had no energy on the floor. Now that it's on the desk, it has potential energy. The only way it gets that is if I give it some. Okay, do I burn some energy doing that? Okay, that's why people work out. Okay, they want to burn some calories or whatever. Okay, they're doing work. They're lifting things and lowering and lifting and lowering, and that takes energy. Okay, you burn those calories. Okay, is all that energy being conserved? Is it all still there? What do you think? It is, but it doesn't always look that way. Okay? The law of conservation of energy says that energy can't be created and it can't be destroyed. That's the first law of thermodynamics. Okay? Is that energy can't be created and it can't be destroyed. But what happens all the time is it gets turned into other forms that are less obvious. Okay? So if you slam on the brakes in your car and come to a stop, you've taken the mechanical energy of your car and you've gotten rid of it. Did you destroy it? No, you can't destroy it. It's still there. What did it get turned into? When you slam on the brakes, what happens in your car? Okay, but why? Right, there's little pads. If you ever look through the wheel on your car, you can actually see the shiny brake rotor, okay? And usually on there somewhere is a pad, okay? And the pad squeezes onto the rotor. So what you would see is a shiny circle, and then in one spot there'll be kind of this kind of shaped thing that clamps down onto the rotor. So they squeeze together like this when you apply the brakes, okay? What's going to happen if these two pieces of essentially metal are squeezed together? It's going to get hot, okay? Your mechanical energy gets turned into heat when you apply the brakes. Okay? We want it to get turned into heat because we want to get rid of the mechanical energy of our car if we want to stop. And the only way to do that is to turn it into something that doesn't involve movement. Everybody follow there? Okay, so your brake rotors get hot. They cool off quickly. They're designed that way, okay, so that they don't stay hot, but they do get hot. And if you ever watch like night racing, you can see in the dark as these cars approach a corner, you'll see like two glowing cherry red circles on each side. Okay, when they apply the brakes, they get so hot they actually glow. Okay, yours probably wouldn't on your car, but you know, in a race car where they're using specialized stuff and they're moving very fast, they get that hot. Okay, they got to get rid of a lot of energy. All right, so we're still conserving that energy. It's still there. It's just changed form from mechanical to heat to sound, in some cases even light if they start to glow, okay, things like that. But we're turning it into forms of energy that don't involve us moving anymore. All right, so the energy of a system can be increased in two ways. Either you can add heat to the system, okay, that is transfer thermal energy to it, or you can do work on it. And if you do work on it, you're adding mechanical energy. So either of those two ways will increase the total energy of a system. Okay. Now, if you do work on a system, okay, that system is gaining energy. That work is considered to be positive because the energy of the system goes up. Okay. If the system does work, then it's going to be negative work because it's going to lose energy. All right. So if I lift something up and put it on the desk, from my perspective, that's negative work because I now have less energy than I had before. I transferred it to something else. Okay. Whereas if a heavy object fell on me, that would be positive work from the object's point of view. Okay, it would be positive work from my perspective because I will have gained energy. Work will have been done on me, probably unpleasantly. Okay, because a change in shape is still counting as work. And if something heavy fell on me, it would change my shape in an undesirable way. Okay, everybody follow? All right, so energy can flow out of a system to its surroundings. That's negative work. Positive work is energy came into the system. Okay, this example here, this girl here is not being very smart. She has a very hot metal rod, and she's holding onto it with no gloves on. That is inadvisable because metal conducts heat very, very well. If the end of it was really hot, so would this end. Okay, but she's put it in this bucket of water. Okay, what's going to happen? It's going to cool off. Energy is going to flow from hot to cold. The water is cold. It's going to transfer energy to the water, and the water is going to increase in temperature. Maybe some of it will vaporize. Okay, all of that kind of stuff that usually happens when you put something really hot in water. Okay, with this guy on the pogo stick. Okay, when he jumps onto the pogo stick, what happens to the spring? It compresses. Okay, is he changing the shape of the spring? Is that work? Yes, because now what does the spring have? It's got energy. Okay, there's two different kinds of potential. Actually, there's lots of different kinds of potential energy, but okay, there's gravitational potential energy, which he would get by jumping up into the air. Okay, when you jump up into the air, okay, you reach a certain height, you have potential energy. When you fall back down, that potential energy turns into kinetic. When he hits the spring, his kinetic energy does work on the spring, so he slows down, loses energy. The spring gains energy, and he changes the shape of the spring. Now, when the spring gets compressed as far as it'll go, it pushes back, okay, and it'll give some of that energy back to him and fling him up into the air, okay, and that's how you kind of jump along on a pogo stick, okay. Do you have to keep putting energy into the spring though? Yeah, you can't just jump onto a pogo stick with one jump and have the pogo stick just bounce down the street, okay, because every time the spring gets compressed, it makes a little bit of noise, it makes a little bit of heat, and energy is lost to the surroundings. So if all you did was jump onto the pogo stick, you might get like 2 bounces or maybe 3 before it just stopped. Okay? It's going to lose that much energy. It's not all that efficient. All right, so the first law of thermodynamics says, okay, that total energy, including heat in a system and its surroundings, remains constant in its system and its surroundings. Doesn't mean it's all staying in the system, okay? But if we can account for all of it, it's always going to be there. Okay? Either it's heat or it's sound or whatever, but it's always going to be there. Okay, so a prime example of that would be like a roller coaster. Okay, if I have a roller coaster sitting at the top of the first hill, not moving, all of its energy is potential. Okay, let's say it has 1,000 joules of potential energy. When it goes down the hill, if it's a perfect system and no energy gets lost, so it's like an isolated system, when it gets down here, it'll still have 1,000 joules of energy. It'll just all be now what kind? What kind of energy has to do with how fast you're going? Mechanical, specifically, starts with K. Kinetic energy. It would have 1,000 joules of kinetic energy. Okay, if I was looking at it up here, it would have some kinetic and some potential because it's a little bit above the ground and it would still be moving, but it would still have 1,000 joules of mechanical energy at that point. Some kinetic, some potential. Okay, that's in the perfect world where it doesn't lose any energy. Okay, if I'm looking at the real world, okay, up here it's got 1,000 joules of energy. Okay, down here, okay, there's 1,000 joules of energy in the system, but is it all in the cart anymore? No, the cart will have lost some, because if you ever stood next to a roller coaster, they're really loud. And not because there's people screaming on it, but because the wheels are metal, the track is metal, there's a lot of friction there, okay, and so it makes a lot of noise. And sound is a form of energy, which means the cart is losing energy as it travels along the track. That's why you never see two hills on a roller coaster the same height as the first. It would never get back up to that height. It loses too much energy as it travels. Okay? That's what happens in the real world. That mechanical energy gets converted to sound and heat and other forms. Okay, that makes sense to everybody there? All right. Okay, how many people have heard of a perpetual motion machine before? Okay, or a perfect machine? Okay, a perpetual motion machine is a machine that could run forever with no input of energy. Okay, it would just constantly run. Why is that not possible? If something's moving, because a machine has to move, what is there always going to be? There's always going to be a loss in energy. Anytime you convert one form of energy to another, energy is lost in the conversion. It's always that way. There's no 100% efficient way to convert one form of energy to another. It's always going to be lost. Okay, so a perpetual motion machine can't be built because there's nothing that's 100% efficient. Even if you could make one, it would be little more than a scientific curiosity. It could never do any work. So even if you could make one that would run forever without having to put anything in, it couldn't do any work. That is, you couldn't attach it to something and say, power this. Because as soon as you plugged it into something else, what would it lose? Energy. Because as soon as you do work, you've transferred energy away and the thing would stop. Okay? That's why all machines that we use are either plugged into the wall or run on fuel. They're constantly turning that energy into what we want. They can't just run for free. Okay? There's got to be some initial source of energy. If you transfer energy away or do work, you'll stop. Okay? So there's no way to make a perfect perpetual motion machine because the second law of thermodynamics says it's impossible. Okay? Energy flows from high energy to low energy. It's always going to be transferred away. And if you make it do any work, it's going to stop. Okay? All right, so looking at these are two ideas people had for perpetual motion machines. Okay, there's this pie wheel, okay, which has these curved things inside, so that as it rotated, the little ball would roll over to the side here, and it would do work on the circle and cause it to spin. And then when they got over to this side, they would roll back to the center. Okay, the idea being that as long as those balls could keep moving, this thing could keep spinning. Except, what's happening right here at the center of the wheel? Is there two surfaces in contact with each other there? Anytime two surfaces slide past each other, you have friction. Okay, and friction is where most energy is lost. Okay, there'd be some energy lost there because there's no way to make that 100% efficient. Okay, so it would lose some energy there. I thought this one had some promise. Okay, using a magnet, so the ball would get drawn up to the magnet and then fall through this hole and then come back down. But it has to open this door every time. If it has to open this door, it has to do Starts with W. Work. And if you're doing work, you're losing energy. Okay. And of course, eventually all magnets do peter out. Okay. It takes quite a while, but eventually you have to remagnetize most magnets. Okay. They're not going to stay magnetic forever. Okay. So does that make sense? You can't make a perpetual motion machine because of the second law of thermodynamics. Okay. Energy is always going to be transferred away when there's a conversion of energy. All right. The idea of a heat engine has always kind of been around. We know the second law of thermodynamics says if I got a hot place and a cold place, energy flows from hot to cold. If I can put a machine in the middle, I can harness that flow of energy and make it do useful work because the energy has to go that way. Right? As long as I can get something in the middle that can catch that, I can use that energy to do work. Now, problem with this. I always have to maintain a high temperature over here and a cold temperature over here. Okay, so that usually means burning something or having something over here that makes lots of heat, okay, in order for this to work. Now, the closer in temperature these two things get, the smaller the flow of energy between them. Okay, eventually, if they got to the same temperature, there'd be energy flowing both directions in equal amounts. Would it be able to do any work in the middle? No, because energy trying to go both ways would cancel itself out. Okay? It only works if there's a big difference in temperature from one to the other. Right? So the idea here, okay, with that, let's say like for the internal combustion engine, okay, when we burn fuel, that makes a high temperature, and that makes the gases inside expand, and that pushes the piston down and turns that heat into mechanical energy and powers your car. Okay? The original idea for a heat engine was for a boat. Okay? The idea being, if I had a pipe that was short and in the warm water near the surface, and a pipe that was really long that ran down further, deeper where the water is cold, the hot water would run through the engine down through this pipe to the cold water and turn the engine. What's the problem with that idea? There's a number of problems. What's one of them? How long does that cold water pipe have to be? Pretty long, yeah, pretty long. Not really practical to have a long pipe extending down from the bottom of your boat. Okay, it's going to catch on things and break off or cause your boat to sink. Okay, so that part of it's not really all that practical. The other part of it is the warm water here and the cold water down below are already in contact with one another. There's something called a convection current going on. Hot water rises, cold water descends. Okay, what's the motivation for it to go through the motor? Nothing. Okay, and what's the difference in temperature between here and here? A couple of degrees maybe. Okay, I mean if you're out in the deepest part of the ocean, then yeah, you might have a difference there of maybe about 20 degrees. Okay, between the surface temperature and temperature of the water, like a mile and a half down. Okay, then there maybe be a 20 °C difference. That's not really all that much in terms of trying to make something like this work. Okay, it does work if there's a massive difference in temperature. Okay, like in a jet engine. Right? Jet engines work because when you burn the jet fuel, it gets really, really hot. And that energy, that heat, flows through the blades of the jet engine, taking air with it, okay, and spinning the blades. And then the blades generate a thrust because they're moving. So as the heat moves through there, okay, it sucks air through with it and blows it out the back, generating thrust that a jet uses in order to move. Okay, so a jet engine really is just a heat engine. Okay, it's a little more complex than the one we saw there. Okay, but in principle, that's what it is. But it creates a huge differential in temperature. Okay, we're talking like hundreds of degrees where the fuel is being burned, and the air temperature at 30,000 feet would be like minus 30. Okay, so we're talking huge differences in temperature. That really enables it to get going. Okay, does that sort of make sense to everybody? Okay, so a heat engine uses the second law, which says heat flows from hot to cold. A heat pump, like an air conditioner or a refrigerator, makes it go in reverse. Okay, so a heat pump is like active transport was in the last unit. It pumps things from low to high. That's what a heat pump is going to do. Okay, it's going to take energy from your food and pump it out into the already warm surroundings of your house. Okay, that's how it keeps the inside of the fridge cold. It takes any heat it absorbs from inside the fridge and pushes it out to where it's already hot, which is against the second law of thermodynamics. You can cheat the second law of thermodynamics as long as you're willing to put in what? Put in some more energy. Okay, you can overcome it if you're willing to put in energy. So what your fridge does, okay, is it's got the little pipes that contain the coolant, or it used to be Freon, it isn't anymore. Okay, as it pumps through there, or as it goes past your food, it absorbs energy from your food, and it changes state from a liquid to a gas. Okay, that gas then gets pumped to the compressor. That's the part of the fridge you can hear when your fridge is running. Okay, is the compressor, and the compressor exerts pressure on that gas and turns it back into a liquid. When you force something from gas to liquid, it gives off the energy it absorbed to change from liquid to gas. So that's the heat you feel coming out from the bottom of your fridge. Okay? It's the energy being released from this coolant that it has absorbed from your food, right? And it's pumping it back out into the surroundings. Okay? That's why you need to keep the door of your fridge shut. If you leave it open for too long, that heat that it's trying to get rid of is just going straight back in. Okay? This is something Homer Simpson discovered the hard way. Okay? There was an episode a long time ago where he couldn't afford an air conditioner. And then he went into the kitchen and he opened up the fridge and he discovered that it was cold inside. So he decided that he was going to take like a bed sheet and put it over top of the fridge and make a little tent. And inside the tent would be cold. Well, what is the fridge going to have to do now? He's got the doors open and he's got this sheet over top. The fridge is just going to run. Okay, and it's not going to shut off because where's it pumping the heat it's absorbing? Into the tent where he's sitting. So it's just constantly running because the heat it's getting rid of is being pumped right into the area it's trying to keep cold. And so it just can't ever achieve the balance it's trying to achieve and the compressor burns out. Okay, most of the time it works because the doors are closed. Okay, it's pumping that stuff away and not having to recool it. All right, an air conditioner works the same way. It takes air in your house, pulls some of the energy out, and then pumps it outside. Okay, it's a heat pump, works exactly the same as a fridge. It's just a bigger scale. All right, so I would like you guys to answer those circled questions there. We're going to be heading down to the pep rally here pretty quick.